My name is Jamie Milliken, and this is Lab 5, Faraday's Law. This is a table of contents. We're going to go over an introduction, the data and measurements, calculations, closed-grip model, and the results/conclusion. So we're going to demonstrate how Faraday's Law relates time-varying magnetic field to a Curly electric field. This creates a current which produces a magnetic field, which exerts a force on the source of the external magnetic field. We will show the effect of Faraday's Law on the motion of a bar magnet through a tube of foil. Two principles we're looking at are Faraday's Law and the Biot-Savart Law. Some assumptions and expectations. The tube is conductive and non-ferrous. It's an assumption, and the roll of aluminum foil will act as a coil of copper wire. We're going to expect that the bar magnet will fall slower inside the tube than it would in a free fall. The system is a tube and bar magnet. The surroundings is everything else. These are the measurements. The average time was 1.29 seconds. Some of the calculations we made in GlowScript include the Biot-Savart Law, which we made a function for. We also made a function for Faraday's Law. We made a calculation for the current in the ring. We also calculated the magnetic force and included the Biot-Savart Law. And finally, the net force calculation, and we did some position velocity updates. Here's the result of the GlowScript model in the picture of the bar magnet, or of the tube. The red represents the counterclockwise current induced in the foil by the north pole of the magnet, and the blue represents the clockwise current induced by the south pole of the magnet. This first question was answered on the previous slide, but the next one is what happens to the dynamics of the system when you flip the magnet around. Basically, the bar magnet's velocity will be affected in the same exact way, but the induced currents will be opposite of what was determined on the previous slide. Next, how does the total time in tube of the real-world system compare to that of the computational system? And how might the computational system be made more accurate? So the total time in the tube in the model was significantly longer than in real life, and that's likely due to errors in calculation of mu in lab 3. In the model, if mu were 2.37 instead of 2.918, the time in the tube in the model would be the same as in real life. And the error also could have been due to inaccurate measurements. Finally, what does the shape of the velocity versus time plot tell you about the forces acting on the bar magnet? So the parts of the plot where we notice changes in the velocity or where the magnet is entering or exiting the tube. These are the areas where there are changes in the net magnetic force. To conclude, what if the resistivity of the conductor were reduced as close as possible to zero? How would the dynamics of the falling magnet change? This would cause the current in the foil to be very large, thus making the time for the magnet to fall through the tube much longer. Next, what if the holes or slots were cut into the tube? How would this affect the ring currents in the model? This would cause the magnet to fall through faster because we would have less rings than in our current model and thus provide less force.